Yes, I think we should start.
Can you see my screen? Can you see the program?
Yes.
Yes, yes.
Okay, perfect. So Alfredo, whenever you want, I mean, it's now 3:31. To keep the time, perhaps we should start.
Yes.
You want to start by saying a few words, then I can say a few words as well?
Yes, the only thing I want to say is that I welcome all the participants in this BS1 session, Scalar Fields in Cosmology, and I wish you to enjoy, or I hope that you enjoy the session, and it is a good experience to do it by Zoom. And okay, have a nice meeting. Thank you.
Thank you very much, Alfredo. So from my side, also welcome everyone to this BS1 session of this 16th Marcel Grossman meeting. And this is devoted, as you know, to scalar fields in cosmology. So let me just add to what Alfredo said with a couple of brief words. At this point, I also invite all the participants to turn on their cameras if they so wish, so that everyone can have a kind of an overview of the session. Firstly, to say that the session is not really limited to scalar fields or to cosmological studies, despite the name scalar fields in cosmology. It also concerns more generic bosonic fields, for instance, vector fields, as well as other applications in relativistic gravity, namely compact objects. Thus, we'll be hearing both about the impact of these fields on the large-scale structure of the universe, but also in localized systems like black holes or putative exotic compact objects. Secondly, to say that the subject of scalar bosonic fields in cosmology or around compact objects seems to be a thriving field with a lot of ongoing work being developed, connected to the latest observations, gravitational waves, shadows, cosmological data, and also a lot of interesting theoretical developments in recent years. So it's really a timely session, I think, and I hope that we will all get something from it. So in today's session, we have 5 talks, and these are the ones that you see in the program, starting with Nico Sanchez Gual, and then João Rosa, then Carlos Hidalgo, then Alexandre Pombo, and finally Fabrizio Di Giovanni. And the BS1 session will have another session later in the week. Okay, so now I invite all participants to switch off their microphones and webcams. Only the current speaker is requested to activate the webcam and the microphone. As well as I'll stop sharing the screen so that Nico can share his screen. So let me just say that the schedule should be respected, and this Zoom meeting will be closed by the organizers 10 to 15 minutes after the schedule. So let's start with the first speaker, that's Nico Sanchez Gual. And Nico will be telling us about light in the dark, GW 190521 as a Procus-Star merger. So if during the session you'd like to ask questions, you can do so by raising your hand, and then we'll pay attention and let Nico know. So without further ado, Nico, please, the floor is yours.
Thank you, Carlos. Can you hear me?
Very well.
Okay, and can you see my slides, right?
Yes.
Yeah, perfect. So, hi everyone. Thank you very much for attending this very nice parallel session. Thank you very much to Carlos and to Alfredo for organizing this session and being the chairpersons. So today I will talk about light in the dark, GW 1905-21 as a Procus-Star merger. So this talk is based on this work that we recently published in Physical Review Letters in collaboration with Juan Calderón Bustillo, Alejandro Torres Forné, Tony Font, Carlos Herdeiro, Eugene Radu, and collaborators. So my name is Nicolás Sánchez Gual. I'm currently a postdoc at the University of Aveiro. I'm a member of the Graph group and also a member of the Virgo collaboration. So let me first try to briefly introduce bosonic stars and ultra bosonic fields, and motivate why it is interesting to study these objects and these fundamental fields in gravity. Then I will present and discuss some of our results on the stability properties and the dynamical properties of isolated bosonic stars, both non-spinning and spinning solutions. And then I will present mergers of these objects and the computation of the gravitational waveforms that we have compared to real events, the W19 of 521, but also other intermediate mass black hole events detected by LIGO, Virgo, and Cadra. So the detection of gravitational waveforms by LIGO, Virgo, and Cadra, together with the first image of the shadow of a supermassive black hole by the Einstein, the Event Horizon Telescope, are opening up a new window into the strong field regime of gravity. But even though the data so far is well fitted by the expected physics, these scale black holes and neutron star mergers, it is important and interesting to understand if alternative non-conventional models of compact objects, this is theoretical exotic compact objects, can also fit the data, or how much these can be ruled out by current or feature detections. So obtaining gravitational waveforms from these exotic compact objects could lead to their discovery if they indeed exist in nature. So among all the proposed exotic compact object models, we in this session, we will talk about the bosonic stars and scalar fields and ultralight bosonic fields. So let me try to answer the question, what are boson stars and why they are so interesting? Scalar boson stars and its vector cousins, known as Broca stars, are made of massive particles with integer spin that follows the Bose-Einstein statistics. So they are made of bosons. At the lowest energy level state, they can be classically described by a wave function, which is characterized by the particle mass mu. And we will see that this particle mass mu play a fundamental role in the description of these bosonic stars. Now we consider a complex scalar field, or in general a complex bosonic field with an harmonic dependence of this type. So to evade stability theorems as the Deriv's theorem for static scalar fields, then we have a complex field with a real and imaginary parts that are oscillating with the same frequency, omega, and the same amplitude, phi naught, but with a pi half phase difference between them. Therefore, the amplitude of the field remains constant with time. So while the field oscillates with a determined frequency, so it's changing with time, it's evolving with time, the space-time can be kept static. This is time independent. And this is because at the level of the stress energy tensor of the bosonic stars, of bosonic fields, it depends on the amplitude of the complex field. So if it is time independent, even if the field is changing with time, it's oscillating, the space-time can be time independent. So bosonic stars can form a stationary soliton-like everywhere regular or isonless solution of the Einstein complex massive Klein-Gordon system for scalar boson stars, and the Einstein complex Broca system for Broca stars or vector boson stars. So actually these objects are minimally coupled to Einstein gravity. So they are described by general relativity, by GR, and they only interact through gravity. It is interesting to know that a real field can also form oscillating with time, can also form massive solitonic solutions that are coupled to gravity, and in this case they are known as oscillators. But the space-time is no longer static, it's no longer time independent, and there is a leakage of the scalar field of the bosonic field towards infinity. So there is a decay of the star which is not as stable. But it turns out that the time scale of this decay of the star can be longer than the Hubble time. So if a real bosonic fields exist in nature, then these objects could have astrophysical relevance. Now let me show you this short movie of the time evolution of the real and imaginary part of the amplitudes of the two parts oscillating with time extracted at some radius for a bosonic star. So you can see that they oscillate with the same frequency, with the same amplitude, but with this pi half phase difference, and therefore the amplitude of the complex field, which is this straight black line will remain constant with time. So we know that regular compact star made of fermionic matter, such as white dwarfs and neutron stars, are supported against gravity by the Pauli exclusion principle, even if for neutron stars it's a bit more complicated. And they are supported against gravity by this Fermi degeneracy pressure coming from this quantum mechanical principle. So can we identify another quantum mechanical principle as the one supporting boson stars, bosonic stars against gravity? So the answer is actually yes. We can identify the Heisenberg uncertainty principle as the one supporting boson stars. So it's the tendency of the field to disperse that will balance the self-gravity of the field itself. And actually, Liebling and Palenzuela, in their very interesting review on dynamical boson stars, they gave an estimate on the maximum mass of a non-spinning scalar boson star derived from the Heisenberg uncertainty principle. And the value is actually very close to the correct maximum mass that can only be obtained with all the fully nonlinear coupled system Einstein complex massive Klein. So you can see that the maximum mass, which is a sort of Chandrasekhar limit mass, but for bosonic stars, depends on the inverse of the particle mass, of the bosonic particle mass. So this means that the lighter the particle is, the larger the maximum mass can be of these objects can be. So if we want bosonic stars in the LIGO, Virgo, Cagra frequency range, this is between 1 solar mass and let's say 1000 solar masses, then this particle mass has to be between about 10 to the minus 10 to 10 to the minus 13 electron volts. So it's an ultralight bosonic particle that gives rise to these massive stars. So boson stars are only coupled to, are minimally coupled to Einstein gravity. I don't know if I say not minimally coupled, but they are minimally coupled. I said that before. So it's GR, they are described by GR. They are only minimally coupled to gravity. So they do not interact with the electromagnetic field. So they do not emit photons. They are basically transparent to the electromagnetic radiation. So we can compute an effective shadow. And actually, we have found that boson and Broca stars can actually mimic the Schwarzschild shadow for some of the models. And actually, you can see Alexander's Pomo's talk for more details on the shadow of Broca stars, mimicking the Schwarzschild shadow. So why studying bosonic stars and ultralight bosonic matter? That's because, well, we know that dark matter is up to 27% of the energy content of the universe, and we do not know the nature of dark matter. So we can speculate, and one of the possibilities that dark matter, or at least a fraction of it, is ultralight bosonic particles. In a cosmological context, scalar fields and even vector fields have been proposed as constituents of dark matter halos in galaxies. If we compute the Compton wavelength for this mass range for a ultralight scalar field, then we get that this Compton wavelength is of the order of kiloparsecs, so of the order of the radius of dark matter halos in galaxies. And it has been shown that black holes, supermassive black holes at the center of galaxies, are actually not a threat to these scalar field dark matter models, because they can develop quasi-bound scalar field or bosonic field configurations that make very, very long-lived, depending precisely on the mass, on the value of the particle mass. It also has been shown by Carlos Herdeiro and Eugene Radu that astrophysical rotating Kerr black holes could have scalar or Broca hair and acquire this hair through the mechanism of superradiance. So actually, astrophysical black holes could become particle detectors that could help us to discover or detect these ultralight bosonic particles if they exist in nature. From a particle physics point of view, there is this axiverse coming from string theory and also coming from quantum chromodynamics, from the action and action-like particles that have been proposed that could have masses between 10 to the minus 33 to 10 to the minus 10 electron volts, which implies maximum masses from 1 solar mass to 10 to the 23 solar masses. So I think it's becoming increasingly clear that bosonic fields, so whether it is scalar field or vector fields, could have a tremendous impact in many areas of physics, namely astrophysics, cosmology, theoretical physics, and particle physics and high energy physics, becoming precisely a link between these different fields. So numerical studies can be undertaken to make predictions and study the dynamical properties of bosonic matter. And in particular, we have been studying lately the stability properties and the dynamical formation of bosonic stars, both boson and Broca stars, both with and without angular momentum for isolated bosonic stars. So if we build the sequence of equilibrium solutions, spherical symmetry, so without angular momentum for both scalar boson stars and Broca stars, so we get these maximum masses. For Broca stars, the maximum mass is slightly larger. And then we have this maximum mass separates the two branches. So we have a branch of models that are stable against linear perturbations, and we have another branch for which the models are unstable. And this is actually very similar to the case of fermionic stars, where we have, so for white dwarfs and neutron stars, we have also maximum masses, maximum allowed masses. For white dwarfs, we know it's 1.4, which is Chandrasekhar limit mass. For neutron stars, it depends a lot on the equation of state, which is still unknown. But we have a maximum mass, and we have a branch of models that are stable against linear perturbations. And actually, so there is this very nice parallelism between fermionic stars and bosonic stars, where we have this maximum mass, and we have also the same stability properties from a linear analysis point of view. So it's not related to the type of matter that we are considering, but to the gravitational properties and the energy distribution. Okay, so then we can address this stability by performing the fully nonlinear evolutions of this system, evolving the Einstein gravity and the boson sector, also for neutron stars. And what we get is that indeed we have models in both cases that are stable, even if we perturb them, and models in the unstable branch that can suffer different outcomes. Namely, they can collapse and form a Schwarzschild black hole. And also they can migrate to the stable branch by keeping the same mass, but also they can, in the case of bosonic stars, they can disperse if they have an excess energy. Okay, but it's not only like studying the stability properties to find that these objects are viable models for their matter. We have to find a dynamical formation scenario that can form these objects. So in 1994, Seidel and Suen found that they could form non-spinning scalar boson stars through the mechanism that they call gravitational pulling. So they started with a dilute cloud, spherically symmetric dilute cloud scalar field, which could have a larger mass than the maximum mass that allowed for these scalar boson stars. Then the cloud collapses. It undergo a gravitational incomplete collapse. It doesn't collapse to black hole, but instead it collapses and forms at the center of the computational grid a compact object that resembles very much to one of the static solutions, static scalar boson star solutions, with the same parameters of mass and oscillation frequency omega. And the excess energy can be radiated away through this gravitational pulling mechanism. In 2018, Fabrizio Di Giovanni and collaborators, we performed the same study, but for vector boson stars, for Broca stars, and found the same results. From the collapse of an initial dilute cloud of Broca field, we can form a Broca star, which is it's perturbed, it's readily oscillating, but around the same static solution with the same parameters of mass and oscillation frequency. So these objects can be formed dynamically from the collapse of large dilute clouds of bosonic field. Let me also add that we can find solutions of mixed stars where we have one part which is a fermion star, for example, a neutron star, and then we have a boson star. So basically they only interact through gravity, so it's a superposition of both fields, of both matter, the boson matter fields, sorry. And we can find and form these mixed configurations which can have different contribution from the fermionic or from the bosonic parts. So you can see Fabrizio's talk later for more details on these objects. Okay, now let's move on to a spin bosonic star. So basically, in this case, so we have that for bosonic stars, the angular momentum is quantized. So it's defined by this azimuthal number, m, which is an integer. So for m equals 0, we have non-spinning solutions, but for m equal 1 and m equal -1, we have the first spinning bosonic star solutions. We can also have excited states, depending on the number of nodes in the radial profile of the bosonic field. But these solutions, basically, there is no models in between this non-spinning and the spinning solutions. So these solutions were found for the PROCA case by Carlos Herdeiro and collaborators and Eugene Radu, and we try to address the stability of these objects. So let me show first the energy density distribution for an m equal 1 PROCA star and for an m equal 1 scalar boson star. You can see that there is this difference. For the m equal 1 PROCA star, the energy density distribution is spheroidal, with the maximum of the energy density at the center, while for boson stars, it has this toroidal shape, has a donut shape. So what we did was we got these stationary solutions of first spinning scalar boson stars, so with angular momentum. This is the energy density profile in the equatorial plane. So we evolve this object, and what we see is that at some point, after a long evolution, there is a non-axisymmetric instability that kicks in and destroys the star. So let me show it again. Sorry. We will see that there is a non-axisymmetric perturbation that grows, and actually the star is destroyed, and because it's compact enough, it collapses to a Kerr black hole. If we try to form this stationary spinning scalar boson star a la Seidel and Suen, this is by starting with a dilute cloud of scalar field with angular momentum. What we see is that because it's the spinning boson star that is formed is less compact, what we see is that fission in two pieces, this bar mode instability that appears, and actually what we see is that all the angular momentum of the star is radiated away through gravitational waves and the emission of bosonic particles, and we end up with a perturbed, non-spinning, spherically symmetric scalar boson star. So it decays from the m equal 1 to the m equal 0 model. Now let's check the stability of spinning PROCA stars. So let's start even with this large non-axisymmetric perturbation for this spinning PROCA star model, to try to trigger some hidden instability. What we see is that it very quickly recovers its shape, this spherical shape, and we end up with this perturbed spinning PROCA star, which doesn't decay. We can even form this m equal 1 PROCA star from the collapse of this cloud of PROCA field with angular momentum, and you can see that at the end of the simulation, we see that we get this profile which resembles this stationary solution with the same parameters of mass, of angular momentum, and of the oscillation frequency omega. So to sum up, basically for m equal 1 spinning PROCA stars, they can be formed dynamically from the collapse of this cloud with angular momentum, and the stationary models, they are stable even if we perturb them with non-axisymmetric perturbations. In the case of m equal 1 scalar boson stars, if we try to form them or not so large, not so compact objects, what we see is that they suffer this fission into pieces, this bar mode instability, and they emit only angular momentum through gravitational waves, and they decay to this spherically symmetric boson star. If it is compact enough, it also suffers this non-axisymmetric instability, and it collapses to a Kerr black hole. So at first, we thought that the stability instability could be related to the type of field. Maybe vector fields give rise to stars, to objects that are more stable than scalar fields. But we also thought that this may be related to the shape, to the morphology, to the energy distribution of the star. Maybe spheroidal with the energy density at the center are more stable than something which is toroidal. We can test that hypothesis, and we found that for m equal to Broca stars, spinning Broca star, actually, they also have this toroidal shape. And what we see is that they also suffer this non-axisymmetric instability. And actually, you see here the bar mode with two maximums of Broca field, and they decay not to the, at least the models that we evolved, they decay not to the non-spinning, so all the angular momentum is not emitted, but to the m equal 1 Broca star, spinning Broca star. So at least part of the angular momentum is conserved and decays to the stable model. So again, let me say that there are also these quasi-toroidal models of neutron stars that rotate really fast, and they suffer this bar mode instability of these m equal 1 instabilities. These are very well known in neutron star dynamics instability that has been intensively studied, the bar mode. And if you look at the evolution of the growth of the different modes of the perturbation, you can see that the m equal 2 dominates, and then it decays to something which is not toroidal by emitting gravitational waves. And if we look now at the time evolution of the modes for a bosonic star, scalar boson star in this case, you can see that the time evolution, the growth of these modes is really, really similar to that of the neutron stars, So there is again this nice parallelism. This bar mode that was very well known for neutron stars also appears in spinning scalar boson stars that are unstable. So it may be not related to the type of matter, but to the energy distribution and also to the gravity of the solution, to the gravitational field. So we also try to a scalar field with nonlinear interaction potential, so 5 to the 4, and we increase the self-interaction term. So by increasing it, what we see is that we can delay the growth of the instability, of this non-axisymmetric instability. And actually was claimed by Simonsen and East that for some critical value of this self-interaction parameter and for different types of nonlinear potential, then they claim that these objects become stable. So with these large self-interactions, we can stabilize these spinning scalar boson stars. Okay, so actually I've said that these solutions come by this azimuthal number m. We can have m equals 0, which are static solutions, m equals 1, which have angular momentum, but actually they can be described by spherical harmonics. So the spherical symmetric solution in a spinning one is the L equal m equals 0. The spinning with this toroidal shape is the L equal m equal 1 or L equal m equal minus 1. But then we can have different type of solution, of scalar boson star solution. For example, this dipole, which is described by the L equal 1, m equals 0 dipole, which is an static non-spinning solution. And we found recently in this paper published in PRL that these solutions are actually members of an extended family of multi-field, multi-frequency bosonic stars. So we can have spinning solutions, also this dipole, and we can combine the different, because they are described by independent complex scalar fields. We can combine them and we can find this kind of family for the L equal 1 solutions. And at the center, we have this enhanced point, which is the L boson star, which is an spherical symmetric solution that comes from the superposition of these solutions, the dipole and spinning solutions, which is static, and both and all the fields have the same amplitude. Okay, so I have discussed the stability of these solutions. We found that spinning scalar boson stars may be without the mini boson, without self-interaction, are unstable. So I studied the spinning Broca stars and Broca stars. So let's put them these objects in a more interesting, from the astrophysical point of view, scenario. This is in binaries. Let's evolve these binaries and let's perform mergers of these objects, and let's compute the gravitational waveforms from these objects. So let me say that the group of Carlos Palenzuela, Luis Lehner, Liebling, Carlos Bona, Miguel Bezares, Paolo Pani, Victor Cardoso have been studying the collisions and mergers of scalar boson stars, non-spinning scalar boson stars. So I focus on Proca stars, on vector boson stars. So the first step is the easiest one is to perform head-on collisions of equal mass non-spinning Proca stars. So you can see here some nice features from these mergers. First of all, the less compact objects will not collapse and form a Schwarzschild black hole, but instead a more massive perturbed scalar boson, Proca star. But if you go to more compact objects and more massive, they will collapse and form a scalar Schwarzschild black hole. Sorry. So we can compare the gravitational waveform from that of an equal mass with the same mass than the Proca star head-on collision of black holes to compare to check the differences between the two signals. So we can have this really different signal compared to the black hole one, but also we can see that we can get the same black hole. So we will mimic the ring down. We will get the same ring down that the black hole collision, but then if we look to the pre-merger, the pre-peak signal, we see that the Proca star has this larger contribution than in the black hole case, which comes from the fact that the two stars do not collapse right after the merger, but instead they oscillate a bit and then they collapse and we have the ring down. I have also performed some quasi-circular mergers where they perform almost an orbit of scalar boson star, of non-spinning ones, but in this talk, I will discuss the head-on collision mergers of spinning Proca stars. So here you can see this head-on collision of two equal mass spinning Proca stars that collapse and form a black hole. And it's important to say that they collapse and form a black hole, so we have the ring down part, because for less compact stars, then we get this type of signal where we end up with a perturbed spinning Proca star that will emit continuous gravitational waves, but not the ring down. So we want to have signals that have this ring down, so we can try to fit real gravitational wave events detected so far by LIGO, Virgo, and Canada. So you can see this head-on collision spinning Proca stars and of Kerr black holes. So basically, head-on collision of Kerr black holes are dominated by the ring down part, the peak and the ring down. But for Proca stars, we have this additional part of the signal. So I've been this last month performing a lot of simulations of head-on collision of spinning Proca stars, equal mass Proca stars, but also unequal mass. So we have now a catalog of around 500 signals from the collision of these objects. Basically, here I will show how the signal, the head-on collision, the gravitational wave from head-on collision changes with the oscillation frequency for the equal mass case. So both stars are described by this omega. So basically, it changes the mass, but this can be the mass of the object, but this can be rescaled. So what it changes is the compactness. The lower is the omega, the more compact is the star. So you will see how the amplitude change, but also the frequency at the different features of the star, of the gravitational wave changes with the compactness of the star. But we always have this ring down part. If we go below omega equal 0.95, then we do not get a black hole formation. Okay, so we have this catalog of 500 simulations, 500 gravitational waveforms from Proca star mergers. So let's try to fit one of the real gravitational events detected by LIGO, Virgo, and Cagra. Let's try to fit them with our catalog. The problem is that, as you may know, that almost all the signals are So it can be explained as a quasi-circular merger of two compact binary stars, or two black holes. So in a quasi-circular merger, what we have is three distinct phases in the gravitational waveform. We have the spiral path in which the objects are getting closer, losing angular momentum by the emission of gravitational waves. So the frequency and the amplitude of the wave is increasing. Then we reach the last few orbits and the plunge and merger that can only be obtained if performed numerical relativity simulations. Then the ring down, the formation of the final black hole, and the ring down path. So we cannot expect to fit these long signals, like for example, the first one, GW150914, which is this chirp type of signal, in which the amplitude of the frequency grows and the peak and the ring down, because our signals, of course, do not have the spiral path. It's just a head-on collision, so we do not have orbital angular momentum and this part of the signal. But there was this new type of signal was reported by the collaboration, by LIGO and the LDK collaboration. It's GW190521, and it's a rather special signal. It's still puzzling, and it's a matter of a lot of debate on the origin of this signal. And that's why, well, first of all, because it's the most massive binary ever detected. It's actually the first direct detection of an intermediate mass black hole. So black holes with masses between 100 to 10,000 solar masses. So this black hole, according to the analysis of the final black hole, according to the analysis of the LBK collaboration, it's 150 solar masses, and it's highly spinning. And it's also the most massive colliding black holes with these masses, and actually this poses a problem because they are inside what is called they are within the pair instability supernova gap. So according to stellar evolution, these masses of black holes cannot be achieved by direct collapse of supermassive stars. So that challenged our models of stellar evolution. It's also an interesting event because there are signs for precession. So the spins of the individual black holes are not aligned with the orbital plane. So they are like this, in this nice representation, this nice illustration. And so we can see in the signal, there could be a sign of precession. So there is a modulation of the signal, of the amplitude of the signal due to the precession motion of the black holes. And if we look at the spectrogram at the signal morphology of GW190521, we compare it to GW150914, which is like the quasi-circular merger signal. We can see that there are these differences. So basically, there is no pre-merger signal. There is almost no inspiral part in the signal for GW190521. We compare it with the first one. So it's like just a burst of gravitational waves with the peak and the ring down. This could be related to the fact that it's the most massive event. So for the larger the mass of the black holes merging, then the lower the frequency of the gravitational waves will be. So for the first event, GW150914 was lighter masses. So we can see in the sensitivity band of the LIGO and Virgo detectors that we can capture, we are sensitive to a large part of the inspiral of the merger on the ring down. But if we go to more massive objects, more massive black holes, then we see that the inspiral phase is behind the low seismic wall, sensitivity wall. So the detectors are not sensitive enough for this low frequency band. But it could be also that the signal is short. Maybe it's not a quasi-circular merger. Maybe it's something different. Maybe it's an eccentric merger, an hyperbolic one. And it's really, there is no inspiral phase. It's not that we are not sensitive. It's just that there is no this part of the wave, of the gravitational wave emission. And it could be, so a lot of groups have been discussing the possibility that this is a merger with eccentricity. And in our case, what we discussed was the possibility that it's a head-on collision of black holes. Actually, we published a paper with Juan Calderón Bustillo, Tony Font, and Alejandro Torres Forné, that discussing the possibility that head-on collisions could mimic precessing signals, because there is, due to the modulation in precessing signals in the spiral phase, then it could be that the head-on collision can mimic these signals. So we tried to fit GW 1905-21 with a set of simulations from head-on collision of black holes, but we found that the head-on collision of black holes can be discarded. This is because if you look at this is the signal from Livingston data. The green one, it corresponds to the head-on collision of two black holes, two paired black holes. So basically, there's no power before the peak, for the merger. It can mimic it can feed the ring down, but not the pre-merger signal, not this part of the signal of the event. So we discussed then the possibility that this could be a more exotic scenario, so the head-on collision of two spinning Proca stars, which is the blue and the red dashed lines here. So basically, because two Proca stars are matter stars, then they will not collapse right after the merger, but instead they will oscillate a bit, and we will have this additional part of the signal coming from precisely this oscillation before the collapse of the star. And then we collapse and form the black hole, and we can get the same bring down with the same mass and the same spin than the ones obtained by the LIGO-BRIGO collaboration. So we did that, and we performed a Bayesian inference analysis to see if this hypothesis would be a good explanation for this event, for the GW 1905-21. And to our surprise, we found that actually the models that we evolved of head-on collision equal mass Proca stars and head-on collision of unequal mass Proca stars, actually they fitted slightly better the signal than the vanilla quasi-circular precessing binary black hole merger that was analyzed by the LIGO-BRIGO collaboration. Even so, according to this Bayesian, it's slightly prefer the Proca star scenario, the Proca star hypothesis, slightly prefer than the quasi-circular binary black hole merger. Of course, this is not strong evidence, but it's quite surprising and remarkable. Then it's like a complex toy model because it's really a head-on collision of two spinning stars. But we can, even with this model, we can fit really well this event. The evidence, of course, is not strong. We cannot claim that we have this event is a Proca star merger, but there is at least this degeneracy in the first time that a degeneracy is really proposed by looking at really performing this standard Bayesian analysis with simulations with gravitational wave coming from numerical simulations of some model that it's completely different to the binary black hole merger. Okay, but even if we cannot claim that it's a Proca star merger, we can assume that the Proca hypothesis is correct, that this is a Proca star, to study if what we can say about these Proca stars. So from our analysis, we got like different masses. Actually, the final mass of the final black hole is slightly, sorry, it's slightly larger than the one than the LBK collaboration analysis, which was 150 solar masses. In our case, it's around 2030 solar masses. It's still an intermediate mass black hole, but we get these parameters for our scenario of head-on collisions of Proca stars. And it's very interesting that we can even compute the mass of the particle, of the bosonic particle mu, which we found to be 8.7 times to the minus 13 electron volt. So coming from this massive event, really luminous gravitational waves, we can say something about these ultralight bosonic particles. So there is this very nice synergy between gravitational wave observations, numerical relativity, also proposing these exotic compact objects in the case of bosonic stars or spinning Broca stars, also studying their stability properties, performing these mergers, and then we can even go to give a number for the mass of the bosonic particle, which we can connect with particle physics and high energy physics. So I think this is a very nice result. So here I show how this is the prior for the posterior for the mass mu of the vector boson particle. So here you can see the oscillation frequency of one of the stars and the oscillation frequency of the other one. So this line corresponds to equal mass, and also this is the logarithmic value of the bias function. So basically, the red ones correspond to the models that we analyze in this paper, and the other ones are the models that we are now doing. We are extending this analysis to more values, to more head-on collisions. So we want to have like the full Broca star model, so we can compare in equal footing with black hole mergers. So this is the update value. It's still preliminary, so we will evolve for more models, but we get a very similar value of the mass, so 8.7 times to the minus 13 electron volts. So this is the masses in the stellar graveyard after the release of GW 190521. So it kind of stands out. This is the final black hole. This is an intermediate mass black hole. So maybe, and only maybe, this event actually is not a black hole merger, but is instead a Broca star or a bosonic star merger. So it's this is the alternative stellar graveyard. So it's this merger of bosonic stars, which are composed by this bosonic particle with this mass. Okay, let me also comment. So you probably know that it was the LIGO, Virgo, and Kaga collaboration put in the archive this paper on the search for intermediate mass black hole binaries in the third observing run of the detectors. So actually there is the second most significant IMBH trigger reported by IMBH, by the LBKC. Yes. So, sorry. So it's this 200114 or the January event, which is actually when it was analyzed with using these black hole quasi-circular black hole binary models. Actually, there is a parametric inconsistency. There is all the different approximants do not give the same parameters of the masses and the spins. So actually, the collaboration cannot say that this is a quasi-circular merger of black holes, but it cannot be discarded that this is actually it's not astrophysical. So it still is not as significant as GW 190521. But so we analyzed this trigger with our Broca star models, and we found that it cannot be ruled out as a Broca star merger. So actually, there's also this. when compare the Bayesian analysis of Broca star models with the binary black hole mergers, actually we get also the same bias factor. So there is again this degeneracy between Broca star models, head-on collisions of Broca stars, and binary quasi-circular mergers of binary black holes. And what we get from the Broca star merger is this value of the mass, which is 10 times 10 to the minus 13 electron volts. So it's very nice that we get, so this in blue, it's the masses, this is the redshifted masses for GW 190521. And our analysis of one is from the LIGO collaboration, and the other one is our analysis with Broca stars. And we see we can match the same final mass, and also for this January event, more or less, we get a good agreement. So you can see that the final masses of the black holes for both events are actually very similar. So we do not, the prior in the final mass of the black hole of the system is what goes from 100 to 500. So our ProcaStar actually recovers these very similar, ProcaStar model recovers these very similar final masses. And if we look at the boson mass of mu, we can see that this is the value we obtained for GW190521. And this is for the January event, and actually they agree inside the one sigma contour interval. So we see that there is an agreement between GW190521 and this January event, at least from the point of view of ProcaStars. So okay, maybe of course there's some differences, but so far, what we have done is to perform head-on collisions, so without orbital motion. This is, of course, a simplified scenario, because head-on collisions, if it's possible in the universe, they will be very rare. So the next step is to do centric collisions and then move to quasi-circular mergers. But for that, actually, we need to solve the constraints. So I've started to do some mergers, some eccentric mergers, spinning ProcaStars. And you can see that actually, if this is the head-on collision, it's a short signal. If we put some initial velocity, some angular motion, then we can get these really different gravitational wave signals. And actually, it is possible that one of these signals cannot be mimicked. I mean, they cannot be imitated by black hole mergers. So if we can detect one of these signals, then we could confirm that bosonic star exists and that this event is really a bosonic star merger and not a black hole merger. So we could break the degeneracy. But for that, we have to build this catalog of eccentric and quasi-circular mergers of ProcaStars. And of course, then go to more complicated scenarios like mergers with precession and with anti-aligned spins and so on, and unequal masses and so on. So let me briefly conclude. We have seen that gravitational waves from bosonic binaries could be used to detect ultralight boson particles. So using real events like GW190521, but also others like the January event 2001-14. But then if LIGO, BIG, and ICRANet detect more IMBH events during 04 or 05, then we could confirm or discard these events as boson star binaries. So at least we can say that GW190521 with this degeneracy has brought us in the realm of what we are observing. Not only if it is a black hole, maybe a quasi-circular merger, maybe a precessing system, or even black hole in a eccentric collision, but even what is the nature, what is the real nature of the objects that they are colliding. Then we have this second low significance trigger that we can also fit very well with ProcaStar mergers. We get the consistent masses at 90% confident interval. So I will finish with these two questions. Is there ultralight in the dark? Is there ultralight particles in the dark that do not interact with the electromagnetic field? And maybe it's time to proc and roll. Thank you very much.
Thank you, Nico, for this very nice overview of the topic and nice results. So we have time for some questions. Are there any questions? You can either raise your hand or you can put it in the chat. I see a comment from João Luís Rosa saying amazing results. Okay, that's
Thank you,
very good. Any further comments or questions? Not really. So Nico, that you gave too much for people to think.
Yeah. Can I add something which I forgot to mention?
I think so. Yes, there's still time. Yeah. There's actually a question also next.
Okay.
But okay. But go ahead, maybe please on your comment, and
Yeah.
then.
So. Okay. Thank you. So just I wanted to say that. So maybe you can wonder why, if this is a boson star merger, are the other events could the other events be a boson star merger, like the other LIGO Virgo events reported? So the answer actually would be no, because I've tried to say during this talk that we can have models that are compact enough to collapse and find a black hole. So in the signal we would have the ring down, but also there are models that are not compact enough and they do not collapse to a black hole. So actually, for the masses that we get for these boson stars, all the other events, if they were boson stars with the same masses, then if they collide, they would not form a black hole. And all these signals have the ring down path. So actually, we can discard if these are really boson star merger, just because of the masses of the different events. Then we can discard them as a boson star merger because of the lower compactness.
Okay. So there's a question by Juan Carlos Hidalgo. Please, Juan Carlos.
Hi. Very nice talk, Nico. Sorry, probably the question I'm going to ask you've already answered, but I had internet problems. But I wanted to ask, like, how stable are these stars against black hole formation from? So at which stage your stars would collapse and form a black hole, or would be unstable enough to form a black hole?
Which stage? But during the merger, the collision?
No, the original stars. So you say that there's a pressure, right? And a lot of people have worked out, say, scalar field stars or boson stars out of, as you said, the uncertainty principle as using it as pressure. But then at which stage, if there is any, or do you think there is any stage at which these configurations would be unstable and collapse to form a black hole?
So, so if they are isolated, then they would be, if they are in a stable branch and isolated, then they will be stable like forever. It's an static solution or a stationary solution, so they do not evolve, and they are, even if you add some perturbation, some linear perturbation on axisymmetric perturbation, the spinning Proca stars that we have studied and performed these mergers, they are stable. They are completely stable. It's not some effective stability. There is a time scale at which they will collapse. No, in this case they are stable.
Okay.
Then there are other models like spinning scalar boson stars that, yes, they can become unstable and they could even collapse to a black hole if they are compact enough. In that case, the time scale, depends on the boson particle mass, which is basically the scaling factor. So it could go, if these stars are like supermassive, then the time scale is years or thousands of years. I think I remember the time scale. If the mass is larger, the mass of the particle, then time scale is reduced.
I see. Yeah, it's inversed with the mass, right? Yeah. Okay, thanks.
Thank you.
Okay, thank you. Any further questions? Well, I don't see any further questions. So if not, let's thank Nico again. So at least I'll clap.
Thank you very much, Carlos. Thank you all.
Nico. And I guess please stop sharing, okay? And we can move on to the next speaker. So the next speaker is João Luís Rosa. João, please, yes, turn on your camera and share the screen. Okay, we can see it. That's good. So João Luís Rosa is going to be telling us about testing the hypothesis of a bosonic star at Sagittarius A star. Okay, so João, please go ahead. The floor is yours.
Thank you very much. Let me just confirm I have 30 minutes, correct?
You have 30 minutes.
Okay, great. So thank you very much. This is a work I have been doing for a few months already in collaboration with Vitor Cardoso and Paulo Garcia from Centre, and also Frédéric Vincent from the Observatory of Paris. Frédéric is one of the scientists that developed the ray tracing code Giotto, and this is exactly why we are collaborating with him, because we make use of this code to make our analysis. So let me start by stating that many of the observations we have today, they seem to imply that objects that behave like black holes exist in the center of galaxies. And two, probably of the most famous examples are the orbits of the star S2 in the center of our own galaxy. And also recently we have seen what seems to be the shadow of a black hole at the center of MET7. So these observations, they are consistent with the predictions of GR from supermassive black holes. And so they seem to indicate that black holes exist. But black holes, unfortunately, they are not just sunshine and rainbows. They have problems. They have singularities, they have event horizons, they have this information loss paradox. And so it would be very important if one could develop some model of an alternative compact object that somehow reproduces the observations we have from the center of galaxies without featuring the same problems. Many different models were proposed, and they can be tested. Now the thing is, most of the objects that were proposed, these are objects that, from the perspective of an outside observer, they look exactly like a black hole. So if you are far away from the object, the exterior metric, let's say, is pretty much close to Schwarzschild, for example, if one considers static objects, or pretty much close to Kerr if one considers rotating objects. So to find and to test the difference between an exotic compact object and a black hole, we need to probe the regions very close to the event horizon, or to the surface of this super compact object. And one of the most, let's say, most popular ways of doing so is via the use of gravitational waves. One can detect, for example, tidal effects in the gravitational waves, the gravitational wave echoes, supposedly, and difference in the phase of the gravitational waves, and also the quasi-normal mode. So this is one very, let's say, very popular way of probing this strong gravity regime, and allows us to test models for compact objects. Now, luckily for us, very recently, just 1 year ago, the Gravity Collaboration has made a very interesting discovery of what seems to be a hotspot, some kind of fluid at a very, very high temperature, emitting radiation near the center of our galaxy. So there seems to be something orbiting at some radius, let's say between 6 and 10 m, the central object in our own galaxy. So somehow this provides us an alternative way of studying exotic compact objects. One can do some ray tracing and simulate the orbits of some hotspot orbiting a central black hole or a central alternative compact object. And one can compare the predictions from a certain model with the observations from the Gravity Collaboration, and use this to impose constraints on alternative compact objects. So luckily for me, Paulo Garcia is a member of the Gravity Collaboration, and this is exactly his task in this work. So this can be used to test many different compact objects. In this presentation and in the work I am conducting now, we want to test if these central objects can be boson stars and protostars. And the motivation for that is that we know that fundamental fields exist. For example, we know that the Higgs boson exists. It is a scalar field with a certain mass. Of course, the Higgs boson is not stable in these conditions. So the boson we are looking for is not really the Higgs boson, but many different models for dark matter object, for dark matter fields, they assume the existence of stable scalar fields and stable vector fields with a certain mass. So in such a way, there is a motivation to study some condensates of these fundamental fields based on models from dark matter. So the two theories we are going to use in this approach are the Einstein-Klein-Gordon theory. This is the theory that couples the Einstein-Hilbert action minimally to a complex scalar field with a given mass. Of course, there can be extra terms like quartic terms, etc. But to simplify everything, let's just consider for now a scalar field with a given kinetic term and a given mass term. And for protostars, we consider the Einstein Proca theory, which is pretty much the same, but instead of a complex scalar field, we have a complex vector field again, just with a certain mass, a certain kinetic term, and no terms with extra, no terms of higher order than that. Now, what we are interested to do is to compute the equations of motion for these two theories in the case of the scalar field and the massive vector field. These are the equations you probably have all seen at least once. This is the Klein-Gordon equation for a massive scalar field, the Proca equation for a massive vector field, and now we check what happens if we look for solutions, for localized solutions of these equations. For those of you who might not be familiar, this is a very straightforward process. We just consider some boundary conditions at infinity that say that the distribution of the scalar field or the vector field decreases exponentially. This guarantees that the solution is localized in a finite region near the origin. And we assume regularity at the center. So instead of having a singularity like a black hole, we assume that the boundary condition at the center says that the amplitude of this extra fundamental field is some certain value, a constant value that is regular at that point. Now, what do these solutions look like? Now, let me show you the, first of all, for the Boson star on the left, and then I'll show you the Proca star on the right, two plots. The first plot is the GTT component of the metric as a function of the radius. The second plot is the GRR component of the metric, again, as a function of the radius, for 4 different boson stars. Now in here, there is a thin black line. I hope you can all see it. This represents the Schwarzschild solution, the GTT of the Schwarzschild solution, and GRR from the Schwarzschild solution. And these 4 boson stars that I'm representing here, they have a different central density. This parameter gamma 0 represents the central density of the Proca star, and there are 4 different values of the central density. The higher the central density, the more compact the star will be. So in principle, as you can see here, for the most compact boson star, the radius at which this star becomes undistinguishable from a black hole, as seen from an exterior observer, happens at a lower radius. Now, these values of the central density have been chosen in such a way that the most compact boson star has a radius of r equals 9m, the second one has a radius of r equals 12m, 15m, and 20m. These are the 4 values of the radius that we are going to study and analyze in this presentation, both for boson stars and the same for Proca stars. And as you can see, well, the metrics pretty much become very similar to black holes when the radius is greater than the radius of the star. So as you can see, for example, here, the radius equal 9m, the first boson star is virtually indistinguishable from a black hole, both in the GTT and also in the GRR. The second one for R equals 12m, 15, and 20m. This is basically what we are expecting. And the advantage of these boson stars is that, as you can see, the GRR and the GTT never diverge. They don't diverge at the origin like it happens for the Schwarzschild solution. They are stable. They are regular at the origin. They approach a certain value and they do not diverge. For Proca stars, the method is pretty much the same. Just the equation is the only thing that's different, because instead of the Klein-Gordon equation, we have the Proca equation, but the method is pretty much the same, and the solutions qualitatively are the same. In here, again, we have GTT as a function of the radius, GRR as a function of the radius, black line represents the Schwarzschild solution, and again, we have F0, which is the central density of the Proca star, and these values of the central density have been chosen in such a way that the Proca star, the 4 Proca stars represented here, they have radii of 9m, 12m, 15m, and 20m, just like the same choices for the boson star. And again, the same thing verifies. So if you are at a radius greater than the radius of the star, then these stars are virtually indistinguishable from black holes. But if you go to a radius inside the star, then you start seeing some discrepancies. By the way, as I said before, the boundary condition at infinity is chosen in such a way that the scalar field decreases exponentially. But the exponential is never really zero, right? So one has to define the radius of the star by assuming a certain quantity, a certain amount of the scalar field inside the radius. And in here, the radius of the boson star and the radius of the Proctor star were defined in such a way that R means that 98% of the total mass of the boson star or the Proctor star are inside the radius of the boson star or Proctor star. Now, these are the solutions for the metric. Let's see what happens if we put an object orbiting this central boson star, this central Proctor star. So in the left now, we have in the first plot the orbital velocity of an object around a central boson star as a function of the radius. And in the second plot, we have the relative error of the orbital period, so period of the boson star minus period of the black hole over the period of the black hole, again plotted as a function of the radius. Notice that the second one is plotted in logarithmic scale. So what do we see? Pretty much the same thing happens again, right? So if the object is orbiting at a radius bigger than the radius of the boson star, then we can see that the orbital velocity is pretty much the same as for the black hole. Again, we have the black line here, the very thin black line here represents the orbital velocity of the black hole. But if you put your object orbiting in a region inside the boson star, then you start seeing discrepancies. The orbital velocity of this object will be smaller than the orbital velocity of the black hole because in this case, there is matter outside the orbit that is not considered when the object is orbiting the central object. For the orbital period, the black line here represents the 1% error. And as you can see again, if you increase, as you increase the radius, the orbital radius, the difference, the error in the period between the boson star and the black hole decreases and eventually becomes super, super small. So in here, it's I plotted this to 10 to the minus 4, but they just continue dropping because the density of the scalar field decreases exponentially with the radius. So as you can see again, if you choose an orbit with a radius greater than the radius of the star, the errors between the orbital periods are super small. If you choose an orbit smaller than the radius of the star, you start seeing discrepancies. For the Proctor star, the solutions again are qualitatively the same. In here, you can see that the orbital velocities are slightly different for the Proctor star than when compared with the boson star, and also the orbital periods, especially the one for the most extensive boson star, the one with the Proctor star with a radius of r equals 20m. You can also see that there is this slight discrepancy here because the period does not decrease linearly in logarithmic scale as it happens here for the boson star, and this has to do with the asymptotical behavior of the metric, which is slightly different than the boson star, but still we can see that the radius decreases, the error decreases as we increase the radius, which is exactly what is expected. Now, enough for the theory. Let's simulate what happens for an object orbiting these stars. So I'm going to present you 3 videos. I want you to start focusing first in this one on the bottom left corner. This is a simulation using Giotto, so the ray tracing software developed by Frederick Vinson and collaborators. In here, we have represented an object. This ball here, this is an object emitting isotropically radiation, and it's orbiting a central Schwarzschild black hole. The orbit radius here is r equals 8m, and in the center you have the Schwarzschild black hole. That's not represented here, but that's the idea. So what happens? There is a primary image. The primary image gets distorted as the object moves behind the black hole. There is a secondary image appearing here that is also super distorted. And eventually, when the object comes back to the front of the black hole, the image becomes spherical again, and the secondary image disappears. Now, if the central object is not a Schwarzschild black hole, but instead is a boson star or a Proctor star, there will be differences. So the plot on the left here, this is a boson star, the most compact one. So a boson star with radius r equals 9m. And again, we keep the orbital radius at r equals 8m. In here, we have the Proctor star also with the same radius as this boson star, radius equals 9m, and an orbital radius again of r equals 8m. So what happens? Same thing happens. The primary image gets distorted as the object moves behind the black hole, but now we have not only a secondary image appearing, but also a tertiary image. And you can check the same thing in here. So the object moves behind the protostar, a secondary and a tertiary image appear, and then when the object comes closer to the front of the protostar again, the secondary and the tertiary image disappear. So what are these images? In the case of the Schwarzschild black hole, we understand pretty much what's happening. So when the object moves to the backside of the Schwarzschild black hole, when the object is behind the Schwarzschild black hole, if the deflection is strong enough, we will see a primary image coming from made of photons coming from above the Schwarzschild black hole, and we will have a secondary image made of photons coming below the Schwarzschild black hole. By the way, I think I forgot to say this, but these images were simulated with an observer looking at the system from an angle of 80 degrees with respect to the vertical axis, to the axis of the axis perpendicular to the equatorial plane. So this is 80 degrees. So as you can see, there are photons coming from above and from below the Schwarzschild black hole. Since boson stars and protostars do not have event horizons, there is an extra possibility. And this is exactly what causes the tertiary image. Not only photons can approach the observer from above and from below this boson star or protostar, photons can actually cross also the center of the object and reach the observer by a third path. And this third path is exactly what makes the tertiary image. So in general, there are many differences between the observations qualitatively, just qualitatively. There are many differences between the observations if the object is a central black hole or a central boson star or protostar. The most visible one, the most important, is the apparition of this third image because these two objects do not have event horizons, but there are other differences. If you look, for example, at the shapes of the images, and this is especially true for the protostar, look at the protostar here, it's going to happen in 1 second, and here it is. The secondary and the tertiary image have a very, very intense flux, and the shapes are larger than what happens for the boson star case, for example. Look at the boson star. When the object crosses below the boson star, we still have the apparition of a secondary and a tertiary image, but the shapes are smaller and the flux is not so intense as it happens for the protostar. So there are these differences are all measurable, let's say. And one fourth difference that is not clear here, but it's going to be clear in the next slide, is the deflection angle. So as you can see, since the boson star and the protostar, they have radii bigger than the radius of the orbit, then the deflection angles will be smaller for the boson star and for the protostar than for the Schwarzschild black hole, because for the Schwarzschild, the entire mass of the system is inside the orbital radius, which is not true for the boson star and for the protostar with this radii. And notice that I choose this particular radii because I know, and everyone that's familiar with the subject knows, that boson stars more compact than these ones start to become unstable. So these boson stars with radii equals 9m, they are more or less in the limit of stability for boson stars. Stars more compact than this might become easily unstable, so these are not the ones we are interested in. So another thing one can do afterwards is to take these orbits and these simulations and integrate the flux for one entire orbit and see what happens. So in here, I present you the integrated flux for an orbit of this hotspot around the Schwarzschild black hole and around the boson star. And as you can see, again, there are differences. One of perhaps the most visible difference is the apparition of this horizontal line here in the flux of the boson star that does not appear in the Schwarzschild black hole. This corresponds to the trajectory, let's say, of the tertiary image in our screen. In the case of the Schwarzschild black hole, although it's not super visible here because of the resolution of the picture, notice that this simulations take some time to do, and in this case, I have chosen to work with images 400 by 400 pixels. But if you increase the resolution, this becomes more clear. In this case, you can see some pixels here. For example, here there's one, but they are not very much visible. This corresponds to the Einstein ring, and it's caused by the presence of the event horizon. Since the protostar does not have an event horizon, the Einstein ring is replaced by this horizontal line. So this is perhaps the most visible difference. This increase in the flux on the left side corresponds to the Doppler shift. And again, and for the same reason, you have a decrease in flux on the other side that corresponds again to the Doppler shift, but in the opposite direction. Another difference that is visible here is, as I was saying before, the amplitude of the deflection. As you can see for the Schwarzschild black hole, this amplitude of the deflection in the secondary image is larger than for the boson star, and the same, although it's not super visible here, the same happens for the primary image, and this corresponds exactly to the fact that not all the mass of the boson star is inside the orbit. Another thing one can test is what happens if we change the radius of the boson star. And this is what happens here. So now I present you the integrated fluxes for orbits of r equals 8m, so same radius of the orbit as we have worked so far, but now for boson stars with different radii. So again, we repeat, this one is the same as this one, but smaller. So this is for the boson star which radius equals 9m. Here we have boson star with radius r equals 12m, 15m, and 20m. And as you can see, this changes. And why does this change? Well, because since we are increasing the radius of the boson star, but keeping the mass of the boson star constant, there is fewer and fewer mass of the boson star inside the orbit. And so the deflection becomes smaller and smaller. And this is exactly what you see here. So as you increase the radius of the boson star, the deflection angles decrease. And the deflection angles in the secondary image also decrease. And they might decrease to a point where at the angle we are observing the system, the deflection is not strong enough to bring to the observer photons coming from below the star. And this is why, for these two particular cases, r equals 15 and r equals 20, the secondary image and the tertiary image disappear, because at the angle we are observing, the deflection is not strong enough to bring us photons from below the central object. And this is also something that can be tested. Now, what's the objective? Now we have done all these observations, all of these predictions. Now we want to compare these with observations. So what are the things we can do? Well, the first thing we can do is to compare our integrated fluxes with the observational data, because the gravity collaboration has computed observed the fluxes, and in particular, they have observed the centroid of this flux. And we can also compute the centroid of the flux in all of our cases and compare with observations. This is the first thing we can do. Now, the second thing we can do, and this is why I've shown at the beginning, or not really at the beginning, maybe at the middle, I've shown you the orbital periods and the error in the orbital periods. Well, the gravity collaboration has also detected, has also computed, let's say, the periods of the orbit of this hotspot near the central object. And since we have the errors between the orbits around black holes and around boson stars and protostars, we can try to impose a constraint on the radius of the central boson stars and protostars based on the experimental error for the period. We know what the period should be. We know what the error of the period is. So within the error of the period, we can impose constraints on the radius of this boson stars and these protostars. And in the same way, since we are imposing constraints on the radius, we are actually imposing constraints also on the masses of the stars. And furthermore, since these stars, these boson stars and these protostars, they are made of these fundamental fields with a given mass, if we have constraints on the radius and on the mass of the objects, the only free parameter that's left is the mass of the fundamental field, because there is this relationship that connects the radius of the star, the total mass of the star, and the mass of the scalar field or the vector field in the case of the protostar. So if we have strong constraints on the radius and on the mass of these stars, we can actually impose constraints also on the masses of the fundamental fields. So these can be used, for example, to impose constraints on dark matter models, because we know that these fields, these boson fields, these scalar fields and these Proca fields, they are massive and they have to be stable. There are no counterparts in the standard model that satisfy these requirements. And so if we are imposing constraints on the mass of these fields, we are actually testing models for dark matter. Finally, There is one last thing we would like to do. We have already implemented this in our code, but we have not tested it yet, which is to test the validity of Newtonian approximations for boson stars and protostars. The Newtonian approximation for boson stars has been published a few years ago. The Newtonian approximation for protostars is now under development by Vitor Cardoso and a collaborator, and I think they should publish it very soon, if it's not already. If it is, I didn't notice. But these approximations have already been deduced, and we have already implemented them in Giotto. So now the thing is, we know that in principle, these Newtonian approximations are not valid since we are dealing with the very strong regime of gravity. We are dealing with objects orbiting the center of our galaxy near a supermassive object. So in principle, these Newtonian approximations will not be valid, but nevertheless, it would be interesting to see at which point they become good approximations, because one can test not only the orbit of an object very close to the center, we can choose our orbit to have any radius that we want. We can put our object orbiting at radius equal 10m, 20m, 100m, for example. And we can, if we have implemented the boson stars and the Newtonian approximations for boson stars, we can test and verify at which radius the Newtonian approximation becomes a good approximation for a central boson star or a central protostar. So this is my work so far. I hope soon we will publish the first work with the theoretical framework, let's say, and these predictions that I have shown you today. In a second paper, we will be working also with the gravity collaboration. We will use their data and impose the constraints I am saying, and hopefully we can take some good conclusions about the possibility, the hypothesis of the objects near the center of our own galaxy to be bosonic stars or not. And eventually, we could also extend this result, the application of this method to other supermassive objects in the center of other galaxies. Thank you very much.
Thank you very much, João, for this very interesting talk. I think we have time for at least a couple of questions. So if you'd like to ask a question, please raise your hand or write it in the chat. So I see there is already a question by Fabrizio Di Giovanni. Please go ahead, Fabrizio.
Yes, hi. So thank you very much, João, for this very interesting talk. I have a very naive question. Like, I was wondering why you chose, for example, 80 degrees for the angle of the observer and a radius of 8m. I mean, is there a reason, or is just an example that you did?
Yeah, the first thing we tried was to make the observations, make the predictions with a radius of 90 degrees. But then we had a small problem. There are two astrophysical objects implemented in Giotto. One is a Gaussian hotspot, and the other one is this spherical object that I've shown. And this Gaussian hotspot is bidimensional. So when we were making the first observations looking at the system in the equatorial plane, this object was invisible because it was a two-dimensional object. So in that case, we decreased the angle to 80 degrees so we could see what was happening. Afterwards, we changed the object from this Gaussian hotspot to a spherical object, and the problem is no longer the problem is gone pretty much, but we kept the observations at a certain angle because they were more the behavior of the photons were more interesting than looking at looking from the equatorial plane, because it ceases to be symmetrical, basically.
Yeah, thank you.
Okay, thank you, Fabrizio. I don't see any further questions, but I can ask you maybe a couple of questions, short ones. Mm-hmm. So the first question is, I guess, well, you're assuming that this source is moving along geodesics. And since it's inside the star, I think this requires some sort of justification because there's an environment in which it is traveling. So that's my first question. How do you justify that the source, unlike in the Kerr case or a black hole case in which it is essentially in vacuum, how do you justify that it is moving along a geodesic? And secondly, of course, I understand you're doing the simplest case, which is static stars, but the structure of time-like circular orbits is quite different typically for the rotating boson stars and protostars as compared to the static case. As you know, there's a kind of discontinuity in the solutions. You go from little m equal to 0 to little m equals 1. So I understand that this is a good starting point, but in order to compare to observations, and given that we all think that black holes rotate, don't you think that it would be more interesting, and eventually perhaps you're planning to do so, to consider the rotating case? So those are the two questions.
Okay. Regarding the first question, of course, there is an environment, and probably the movement of the hotspot is not going to be geodesic, which is pretty much what is observed. There is not really a precise orbit around the center. We just have the areas are super large, so it's actually hard to verify if it's geodesic or not. But in principle, it's not going to be. And but our approximation here, I think it's based simply upon saying that these objects, they are made of some kind of a fundamental field that is dark matter, let's say. And in principle, the interaction between the object that's moving around the center and the fundamental fields that compose the central object is really small, to the point we can approximate the movement to be geodesic. As for the second question, yes, indeed, the objective afterwards would be to generalize this for rotating stars, but unfortunately, the implementation of these boson stars in Geo2 is a little complicated, so we decided to start with the simplest possible case of static solutions. I had to learn how to work with the code as well, so it took me a while. And at the moment, after we finish this this part, the objective is actually to not only to generalize what we have for rotating boson stars and protostars, but also to test other types of compact objects. But that's exactly the point.
Okay, thank you very much, João.
Thank you.
Any further question? I don't see anything, so I guess we can finish here. Thank you again, João, for your talk. Okay, and I guess we should move on to the next talk, and that is by Juan Carlos Hidalgo. Juan Carlos, please share your screen and show yourself.
Yes. Hello.
So Juan
Can I
Carlos
share my screen?
is telling us about primordial black holes in a scalar field-dominated universe.
Can you see my screen now?
It's starting, but I cannot see it yet. It says Juan Carlos Hidalgo has started sharing, started screen sharing, but I'm not seeing it yet. Can you see it, Alfredo?
Oh, okay.
Ah,
There?
here it is. Perfect.
Sorry, I posted incidentally. Sorry. Hey, so shall I start now?
Please, go ahead, please. Floor is yours.
So let's switch gears a little bit, although not too much, because I'm going to talk about scalar fields. So my name is Carlos Hidalgo. I come from ICF UNAM in Mexico. My collaborators in this work are Karim Carrion, my student, and the postdocs Ariadna Montiel and Luis Padilla. Let me introduce a little bit about inflation and what is reheating and why we care about primordial black holes in this case. So primordial inflation, as we all know, is the big paradigm to describe the pre-Big Bang stages. There are several models that describe inflation, and typically what we have is a slowly rolling scalar field that goes down its potential, and it generates some quantum fluctuations that would form this scalar field, and would, because of the expansion, would stretch out of the horizon, would spend some time outside the horizon, then re-enter the horizon and scales that we observe today. So for example, for the CMB, what we have is that we can observe scales that have not entered the horizon at the time of recombination. And in that case, what we have is evidence of a primordial amplitude of fluctuations. And this is probably the biggest success of inflation. The success is that the amplitude of these fluctuations indicates that the energy scales of inflation are consistent with the theory of having stages before the hot Big Bang. However, that success is also a drawback because we don't have a single model for inflation. We have several models because we can only probe a few scales for the primordial fluctuations. So as you can see in this picture, this is matching or reconstruction of the power spectrum. The power spectrum is described by a certain amplitude and the scale dependence pivoted by this K star scale, and with a tilt described by this spectral index. But the scales that we can where we can really observe or probe directly the power spectrum are in a very small range. So this is about 1 order of magnitude for K modes, whereas we could have tens orders of magnitude on the universe that entered the horizon from the end of inflation until now. So what we observe really in this scale in this chronogram of the universe is only these two, or these latest scales, which are the largest scales in the universe. We have evidence of what happens physically in all these scales up to nucleosynthesis. Before nucleosynthesis, we don't have really much information, direct evidence of what happens in the physics. We can only speculate what happens here. So from the end of inflation, which is from this moment up to 3 minutes of the universe, we don't have much of a direct evidence of what happens. And there is where the primordial black holes could exist and tell us something about the early universe. Well, this is just to describe the power spectrum. What happens, the other drawback for primordial inflation is that we have put a model or a mechanism that happens before the hot Big Bang, but the transition between that mechanism and the hot Big Bang is not very clear, and that's what we call reheating. So reheating or preheating is a period of transition between the scalar field and standard model particles. And it turns that one of the more efficient ways of doing this transition is by parametric oscillations, as when you swing in a swing, you push yourself so that the amplitude of the swing is larger and larger. In this case, the parametric oscillation of an inflaton field, which in this case is phi, with extra fields of, say, the standard model like the Higgs boson or other particles, if they oscillate together, then there's going to be an efficient energy transfer, as I show here, which is the occupation number of particles of the chi field. In this case, there's several stages at which the inflaton or the other fields, scalar fields, could be oscillating in the bottom of their potential, or even if it's a false vacuum. But the point is that there's stages in which the equation of state is on average 0, and that gives us a chance to have pressureless stages which are suitable for primordial black hole formation, as I will argue in the following. So the standard PBH scenario is one where black holes collapse in the hot Big Bang stages. The formation of black holes are simulated through general relativistic hydrodynamics. So this takes spherically symmetric configurations that would evolve solving the full GR equations from a configuration that would have, let's say, an overdensity. In this case, I show what happens to an overdensity that does not form a black hole, but it's quite impressive how from this year things moved into a more sophisticated simulations that show how the dissipation of these overdensities can happen and simulate, say, or look like waves in the space-time. When a black hole forms, however, the Misner-Sharp radius does get up to a form or to match the Schwarzschild radius, and in that case you can capture an apparent horizon, and you can capture that for several Hubble times and then make sure that what you form is an actual black hole. These studies of what would be the actual configuration that forms a black hole rely or require the study of critical collapse in environments of the early universe. And probably the modern studies of these, or the modern techniques to study this sequence, come from this paper. So in what is actually in detail put in these simulations, we have an initial growing mode and nonlinear overdensity that starts outside a cosmological horizon and then under its own gravity starts collapsing. And the numerical evolution through the solution of Einstein fields equations picks specific density profiles that will get to form an apparent horizon. In that case, we want to know what are the minimal amplitudes in order to collapse, because those are the ones that will get to form black holes. And these are the critical values for the overdensities. As you can see, this is the overdensity value and as a function of the equation of state of the background. So typically in the hot Big Bang, we have ultra relativistic particles that would have an equation of state of about 0.3. In that case, the critical collapse value for the primordial black hole formation would be of about 0.4. That means that your overdensity needs to have an amplitude of 0.4 at the horizon crossing, at the Hubble horizon crossing, in order to further collapse into a black hole. This is just an illustration of what has been done for several profiles of the overdensity. And these kind of simulations have also been reproduced, or these kind of results have also been produced through analytic studies. The first study was done by Bernard Carr in long time ago, where he takes just the linear perturbations in a fluid dominated universe. So the fluid dominated universe, it's described only by its equation of state, and the perturbations of matter follow this kind of equation where you can read Jeans instability scale, and that Jeans instability scale through the interpretation of the top hat collapse can be transformed, or the criterion that the maximum radius of the top hat collapse should lie above this Jeans scale, then brings you to a criterion for what would be the critical value of the overdensity. So that critical value tells you that your overdensity should be above the equation of state value, which is about 0.3 in the case of radiation. But in the case of, but if you want to go a bit beyond that, what this paper does is that it studies the top hat configuration and compensated top hat configuration, which shows an overdensity followed or surrounded by an underdensity, which should compensate the overall density and show no back reaction to the universe. And in that case, what you would have is the collapse of this central region and a threshold amplitude only if that collapse is faster than the travel time of a sound wave through the configuration. So that's a nonlinear study, and in this nice paper, the authors derived this formula for what would be the critical collapse value. Their critical collapse value is this solid line, and the results of the previous slide of the critical amplitude are showed in dots here. So the match is very good up to at least the radiation stages or radiation equation of states. And so you can see two things here. One is that the amplitude for collapse is required to be very large. The other one is that when the equation of state is softened and it's lowered to 0, then your amplitude for collapse in principle shouldn't be too large in order to form a black hole. So that's the main caveat. The caveat is that you need a very large amplitude for perturbations to collapse if you're in an environment dominated by radiation, because then your equation of state is very large, it's about 1/3. And the mean amplitudes observed in the CMB, although far in scales, are of the order 10 to the -5. So that's a big drawback, and these are 4 orders of magnitude away. So we need to change the models or to look for alternative scenarios if we want to have a copious production of primordial black holes. And in that case, people have come up with several ideas: spikes in the power spectrum at small scales, which are away from the observed CMB scales, and then amplitudes that would match these required critical value, or a very large positive running of the spectral index, which would bend the power spectrum in small scales and would give you very large amplitudes, again, at the end of inflation, or look at the phases where the equation of state is around 0. One of those phases, very attractive point, is the QCD phase transition, because the size of the configurations that would collapse to form black holes would be actually of about 1 solar mass. And the other scenario where you can look at things that would collapse is reheating. So let me jump into what would happen for primordial black holes in the scenarios of reheating. The first statement that one can do in the reheating scenarios is that these oscillating phases appear when the mass of the scalar field is much larger than the Hubble parameter. And in that scenario, if you solve the Klein-Gordon equation, then you're going to find that your scalar field is going to oscillate so that it mimics a dust scenario. So that's the first step. And you would say, well, then now I have a dust background and I could collapse anything into a black hole. Well, not really. You can solve the perturbation equations in terms of the Mukhanov-Sasaki variable, and the Mukhanov-Sasaki equation then tells you that for a real scalar field, you will end up with a Mathieu-like equation. So Mathieu equation is one where the Jeans instability is not that straightforward. There's an oscillation of these terms where A is a factor that a polynomial that gives you a factor of k squared. So that's where the modes lie. And then the Q is it's a factor that tells you about the physics in the end of inflation. So this Mathieu equation, it naturally presents through the Floquet analysis an instability scale. That instability scale tells you that modes that lie within or above the square root of 3hm are unstable. That can be translated into a Jeans instability scale, and this has to be taken with a pinch of salt because this is not a fluid, but you can associate a scale for instabilities and think that any stability above that scale would collapse and form either a boson star or a black hole in our case. So that's something that we have not totally determined and is not completely determined, but these papers have, and others of course, have argued that what you would form above this instability scale is a black hole. This is the case of a real scalar field. Now, in the case of a complex scalar field, you have something similar, but not quite the same. The instability is actually at smaller scales. And we found in this recent paper that the instability band is broader. So in this diagram, I show what are the number of K modes that can fit within the instability band in both the real scale and the real scalar field or the complex scalar field cases. What we do in a way is not to take the full solution for the complex scalar field, but one which matches the spectrum expected at the end of inflation for fluctuations. And that was a big argument with the referee, but at the end we won that argument. And then in any case, what you have is an instability band within the modes that enter the horizon just after the end of inflation. And those modes will be unstable down to a certain value, in the case of the real scalar field down to the Mathieu instability scale. And in the case of our complex scalar field would get down to this Jeans scale shown here. And this in a way is also happens because there's no oscillations in some of the observables for the complex scalar field. To construct, for example, the Hubble parameter, what you need to do is to multiply the field times its complex conjugate, and you're going to get no oscillations in what would be the evolution of the Hubble parameter. Whereas in the real case, you have all these oscillations, not only in the Hubble parameter, but also in other observables. And then that gives you an important difference at the level of Mukhanov-Sasaki equation. So what do you do with this scale? I mean, you have now a bunch of unstable modes that could or could not collapse. You need a criterion for them to collapse. So in our case, what we did in a first approach in this paper a few years ago was to transform that instability scale and follow the Harada argument to derive a critical value for the collapse. So in that semi-analytic study or approximation for the collapse, we find that the value of the collapse threshold is very low. So it depends on the square root of h over m. But as I told you, in these stages, h is much smaller than m to guarantee the oscillatory behavior. And in that case, what you have is a threshold amplitude that's very small and surprisingly small, and is smaller than the average fluctuation values. So that means that everything would collapse into a black hole. Because we know that that could not happen, we can impose some criteria that would restrict which configurations can get into black holes. And then there's this sphericity criterion, which tells you what overdensities would be spherical enough to collapse and form probably a black hole. Even so, this beta, which represents a kind of density of the universe in terms of black holes, or fraction density of the universe in terms of black holes, is something that scales with the power spectrum. If you consider a scale independent power spectrum, even one that doesn't give you larger amplitudes at small scales, this amplitude would be about 10 to the minus 10. That 10 to the minus 10, the square root is 10 to the minus 5. The fifth power of that is 10 to the minus 25. The factor here is going to give you a 10 to the minus 27, and that's where this band would predict the formation of primordial black holes. Now, these are constraints of how many black holes you could have because of what we observe in terms of gamma rays of possibly evaporated black holes, both in the galaxy or in the extragalactic background. So that would mean that there's scales at which we could have overproduction of black holes, mainly in scales where the thermalization or the transition between reheating and Big Bang and hot Big Bang happens in these energy scales. So that was a nice result. And when we got to the complex scalar field case, we thought, well, maybe that's not the best criterion to take on account what would happen to the scalar field, because as I said, the scalar field is not fluid, so I cannot really take a gene scale as a criterion for a critical value for the overdensity to collapse. On the other hand, what we could do is to follow the overdensities, follow the linear evolution of overdensities, and then take the top hat collapse criterion of knowing that a nonlinear configuration is going to collapse when the linear density reaches this critical value of 1.68. So this doesn't tell me much about the amplitude of fluctuations at horizon crossing, but I need to follow the fluctuations up to this value in order to take them as configurations that would collapse to form primordial black holes. In that case, we would have, again, large contributions or large fractions of black holes in terms of the overall density of the universe. So this is a range of values for masses, for end of inflation H values, or the number of E-folds that the scalar field would be oscillating at the bottom of the potential from the end of inflation, say, until it has transferred all its energy to another field. So in this study, what we do is we think, well, this is a very large fraction to have black holes, and these black holes are going to be very tiny. So the mass of the black holes gets up to about 10 to the minus 3 grams, and that's not very far from the Planck mass. So they're going to quickly evaporate and hopefully or probably leave a Planck relic behind. In fact, there's a paper about Planck relics today out. I haven't read it completely, but that's a subject of study. And those relics could go and form or constitute the dark matter of the universe. So we have a constraint on how many black holes we can have at this reheating stage. And that constraint comes not only from the gamma rays that I mentioned before, but also on the fact that the relics of the evaporation could form the dark matter. And in that case, we can constrain what is the stage at which the reheating takes place, that is the Hubble parameter at the end of inflation, or the time that the reheating lasts, that is the number of E-folds until the transition to the Big Bang happens. So these kind of criteria has also been used more recently by these other papers. And we take that criterion to constrain what would be an oscillating complex scalar field. And we have put the results in this paper. We can constrain a large portion of the parameter space. And we can show that, for example, you can, all the region above this curve is excluded. So if you have the end of inflation at about 10 to the minus 3 Planck masses, and your oscillation period lasts only for 1.5 E-folds, then you would form, we argue, too many black holes to constitute all of dark matter today. So what's the catch here? The catch is, again, we don't have a definite criterion for when primordial black holes are going to form. So the collapse criterion is lacking. We need numerical simulations for the spherical collapse of the scalar field, both in the real case and in the complex case. And as we heard before, we also could extend things to other kinds of fields or interactive fields. The initial conditions, so how would this numerical simulation operate? We need initial conditions at superhorizon scales. We need an initial growing mode so that we don't dissipate the field. We need certain code, possibly in the BS1 formalism, to collapse these configurations. And that would yield, hopefully, the true threshold amplitude to form these objects. Well, the news is that we have now first step in this direction. Today, there's a paper that we put out in the archive where we solve the gradient expansion of the Einstein field equations up to order h over m squared and up to order gradient over h squared as well. And we recover what's the expected linear fluctuations behavior. So we recover in two examples, the quadratic and the quartic case, what's the linear density growth of fluctuations. But these configurations will be highly nonlinear. It's just that they are well outside the horizon. We can truncate the Einstein field equations to solve this analytically. So yeah, we have basically initial conditions for a code, and and we are now working in doing this code in order to derive the true amplitude for the primordial black hole formation. So that's basically it. We know that the Mukhanov-Sasaki variable instabilities allow for structure formation. We're not sure whether if that could be or not primordial black holes yet, but in case they were, they could form from these overdensities, then evaporate and generate products that are direct observables of reheating. So that's where the important lies. And in that case, we could impose cosmological constraints to either low energy phases of the reheating or long-lasting preheating periods. Hopefully these could be detected as standard sirens, and then we would have yet another observable. There's also the possibility of observing directly the gravitational waves if their amplitude is too large also at the end of inflation. But that's where I shall stop, and I leave you with my references and my contact details. Thank you.
Thank you very much, Juan Carlos, for this interesting talk. We have time for at least one question. So if you have a question, you can raise your hand or you can write it in the chat. I do not see any questions so far. Well, it seems there are no questions. In that case, let's thank Juan Carlos again for his talk.
Thank you.
And we can move on to the next talk. That is by Alexandre Pombo. Alexandre, are you around?
Hi.
Okay, so please share your screen.
Can you see?
Yes, we can see your screen. So
Okay.
Alexandre is going to be talking about the imitation game, broken stars that can mimic the Schwarzschild shadow. So the floor is yours. Please go ahead.
So, good afternoon, everyone. My name is Alexandre Pombo, and today I'm going to present you my work entitled The Imitation Game, broken stars that can mimic Schwarzschild shadow. Well, with all the new current observational evidence for the existence of black holes, in particular the image obtained by the Event Horizon Telescope and the detection of gravitational wave by binary black hole mergers, one question arises. Are all shadows black holes? Well, one of the observational black holes characteristics is the presence of a light ring and an accretion disk. Light rings have been shown to be a generic feature of stationary black holes, where they have an important impact on the ring down and black hole shadow. One other interesting object is known as a Boson Star, which is an hypothetical astronomical object formed out of bosons. For these stars to exist, there must exist one stable self-interacting boson. And usually, compact boson stars are studied involving massive complex scalar fields with a U1 gauge field, which gives a kind of time frequency oscillation. They are gravitational solitons and may be described as everywhere regular lumps of ultralight scalar or vector bosons. In addition, which is very interesting, is that boson stars can be viewed as possible dark matter candidates. They will be transparent and invisible. And due to their immense gravity, their own interaction will be through the gravitation field, and will be able to bend light and create an accretion disk. So what we want to find is if boson stars are good black hole mimickers. Well, if the source of light in the vicinity of a boson star has the same morphology as it will have around the black hole, then we expect that our observational image will be similar. For a black hole, what is the key feature is the presence of a cutoff in the emission disk of the accretion disk, which is known as the innermost stable circular orbit, or ICRANet. However, for a spherical boson star, there is no ICRANet. There are time-like circular orbits everywhere until the center of the boson star, which creates a problem that we have to solve. Well, recently, general relativistic magnetohydrodynamic simulations have shown that the angular velocity of the particles on the orbit of a boson star maintains a maximum at some radial r omega, where this r omega can have the same scale as the one observed for the ICRANet, and then can introduce an inner edge of the accretion disk around the boson star, which raises the problem. So boson stars are then possible black hole mimickers. And this is the objective of this work, is to assess such possibility. For this, we'll consider the usual Einstein matter action, where the matter part is discovered by the spin 0 or 1, and is minimally coupled to the Einstein gravity. For the matter Lagrangian, for the scalar field, we consider a scalar field Lagrangian which contains self-interaction potential U of I. For the vector field A, we consider a Lagrangian that has a self-interaction potential V of A squared, where A squared is the contraction between the covariant and contravariant vector potential A. Now, for the metric ansatz, we consider a standard spherically symmetric metric compatible ansatz. For the scalar field phi, we consider a term with an harmonic time dependence, where the curly phi term corresponds to the scalar field amplitude. we have to consider two functions, f of r, g of r, where the radial component will be imaginary. Now, for the potentials, we consider a polynomial potential, which has the first term, which is a quadratic term, for which it is usually known as mini Boson star. For a quadratic, we also introduce a quadratic potential, which we'll call self-interaction potential, and a sexy term, which is also known as self-interaction. However, since this potential is known to endow cuboles, and to distinguish between the quartic potential, we'll call it Q star or Q potential. In addition, we will also consider an axionic-like potential, which from the plot, you can observe that for small scalar field amplitudes, it's very close to the polynomial self-interaction. However, as we go further from the origin, it tends to have an oscillating behavior, which can introduce some interesting characteristics. For the mini boson procastar, for the procastar, we consider a potential that creates mini procastars and self-interaction procastars. Now, the solutions were obtained with an in-house developed integrator that consists on a parallelized adaptive step Hankuta method, where the proper boundary conditions were implemented through a second strategy. Now, the radial geodesic equation for a particle around the Boson star is given by the following equation, where E is the particle's energy and L represents the particle's angular momentum, where K is a parameter that, if it is zero, characterizes a null geodesic, and if it is equals to -1, characterizes a time-like geodesic. For a circular orbit, the radial velocity is equal to 0, and the radial acceleration is also equal to 0. This means that for the null geodesics, we obtain the following condition. And this condition has two roots, as it was shown, one stable and one unstable. In this case, what we want to obtain is the first boson star that contains a light ring. And this means that the solution will only have one root, which means that the light ring will be degenerate. These solutions are also known as ultra-compact boson stars. Now, concerning the time-like circular orbits, from the time-like geodesic, we can obtain the angular velocity of a particle around the boson star, which is just metric dependent, as before, which is what we expect, because particles move in geometry. As I already mentioned, boson stars do not have an ice core. However, there is accretion disk may have an inner edge even around boson stars, which occurs if the angular velocity of the time-like circular orbit attains a maximum at some radial distance. And here in the plot below, we can observe such profile of the angular velocity. Well, we can observe three, but let us focus on the bigger one, the blue and the red one. The blue one is the profile of the angular velocity of a time-like circular orbit, which contains a maximum outside the origin. And it is at this maximum that you'll have this R omega and the inner edge of the accretion disk. While for the case of the red curve, the maximum is at the origin and will not have an inner edge of the accretion disk. No, but now we have one question that we have to solve, which is if this scale is similar for both boson stars and Schwarzschild black holes. To keep that in mind, we'll introduce a dimensional parameter epsilon, which is a ratio between the radius of the ice core for an equivalent Schwarzschild black hole over R omega. But we have to take into account that we want that such solutions to be inside the stable branch of the boson star. And the stable branch, so here we observe the domain of existence of a boson star, and the stable branch goes from omega equals to 1 until the first maximum of the mass. And we want to see if the solutions are in that branch. Well, the thing is that the mass, and frequency undergo oscillations as we go inside the spiral. However, the field amplitude at the origin grows monotonically. So this means that such parameter uniquely label such each solution, and we can use it to see if we are getting closer or not. For this, we'll introduce the dimensional parameter key, which is just the ratio between the matter field amplitude at the origin over the matter field amplitude at the place where the stability cross exists, which occurs for the maximum mass. With this set, if epsilon is 1 and key is smaller than 1, then we have an accretion disk that has the same scale as the Schwarzschild black hole and is in the stable region. Now, let us study our numerical results. Well, let us start by the mini Boson Star case. For this case, what we observe is that the first ultralight, ultra-compact solution is well inside the domain of existence spiral, and then it's not in the stable solution. In fact, we can observe that for all solutions this occurs, and we are not expecting that any stable boson star to have a light ring. But concerning the accretion disk, well, for the mini boson star, we can observe that it is still far from the stable region and that the scale for epsilon minimum is still very large. If we introduce a self-interaction, a positive self-interaction, we can see that there is a tendency to get closer to the stable region and a decrease in the scale. If we consider, on the other hand, a negative coupling self-interaction, we observe the opposite behavior. We observe that the solutions tend to go away from the stable region. What we can do then is to introduce the Q star potential, and we observe more or less the same. So to isolate this potential, we will consider a solution with lambda equals to 1. And for this case, we observe the same as before. Solutions have a distance larger than 2. But then for a large gamma of the Q potential, we observe then a decrease and the tendency to go to the stable region, and also a decrease of the scale. While for the negative one, it tends to decrease again. It tends to go away again. And as we can see, the first light ring is well inside the domain of existence. In addition, we can also observe that the sextic term, which is just a curiosity, but it's, I think, interesting, that the sextic term has a smaller contribution to the overall shape of the domain of existence than a quartic term, which is to expect, because the scalar field, it's always smaller than 1. So the sixth potential will have smaller impact than the quartic one, and even less than the quadratic. Now, with these results, what is left is that it suggests that a simultaneous increase can indeed obtain the solution that we want. So to test this hypothesis, we consider a solution with lambda equals 100 and the gamma equals to 1000, the two largest values for which we can obtain stable solutions and that the code is viable. And for this, we can observe that chi gets closer to the stable solution. However, R omega is still fairly below the ISCO radius of a comparable black hole. It's still larger than 5. So at least from these parameters, we cannot obtain any Schwarzschild mimicker. The other potential for the scalar field that we used was the action scalar. Well, for the large coupling for a large action coupling, the solution tends to a mini Boson Star configuration, and even for a fairly small, like 0.1. However, if we decrease further the coupling, we observe an interesting property, is that there is a surge of a new maximum of the mass. And with this surge, there is also the emergence of a second stable branch. However, the first ultra-compact object is still far from this stable branch. However, if we consider the solution with an accretion disk, an inner edge of the accretion disk, we can observe that in this branch, there is indeed solutions. They are energetically stable, but the scale is still larger than 1. However, this allows for the possibility of new solutions, even though that our code cannot generate solutions with a smaller coupling. These couplings these domains of existence become chaotic. However, it is interesting, and I want to thank Nicole Sanchez-Guo that it is possible to do a time evolution of such solutions and observe that solutions are indeed perturbatively stable. So there is the possibility that such solutions exist. Now, for the Procastar, we can consider mini Procastar, a Procastar with a negative self-interaction coupling and a positive self-interaction coupling, where the latter, due to the fact that the f of r function has to have a node, has a maximum of the domain of existence. So there is a stop, and that's why we cannot go to larger self-interactions. However, the first ultra-compact object still occurs in the unstable region. But for the case of the Procastar, there is one interesting property, even for the mini one. So if we go, as we go inside the spiral, what we observe is that R omega comes from very large values to 0, and it stays 0, and then at some point has a transition again and starts to have some finite values, where this later part is exactly the same as what occurred in the scalar boson stars. But now for the Proca stars, we have this first branch, and this first branch is exactly in the stable branch. And since this is a continuum, it comes from a very high value to 0, there is a place at which it is equal to 1. So what is left is for us to compute some shadows. Well, first of all, I want to give thanks to Pedro Cunha, which allowed us to study this. And we can observe we have then two configurations. First, imagine that this is a black hole and is surrounded by a accretion disk. And we can look to the black hole from above, perpendicular to the accretion disk. In this case, what we will observe is a shadow that is surrounded by a ring of matter that emits light. And it's what truly we observe from a black hole. We have a shadow that is surrounded by an accretion disk. For the Procastar, we observe exactly the same. We are an inner shadow with an accretion disk, even though there is some difference in the inner edge of the accretion disk. The other way that we can look at the black hole is parallel to the accretion disk. In this case, what we observe is the shadow, the accretion disk, and then since this is a black hole, which is ultra compact, we can curve light. We will also be able to observe the accretion disk that is behind the shadow of the black hole, since the light curves itself over the shadow, which is, again, indeed what we observe for black holes. However, for the Procastar, since these solutions are very dilute and are not compact enough, they are not ultra compact, they do not have gravitational pull enough to curve light. So what we will observe is just the accretion disk. There is no halo around the shadow, and this distinguishes between the two. So, to conclude, well, models with dynamically robust spherical boson stars can mimic the shadow of Schwarzschild black holes. That's what we saw. However, in the case of spherical stable scalar boson stars, while the polynomial self-interaction cannot easily solve this issue, the axionic model may be able to. On the other hand, for spherical Procastars, we found that the simplest model can indeed mimic a Schwarzschild black hole. However, remark that despite the matching between R omega and the ISK of the black hole, we observe that the lines in the different spacetime geometries leads to a slightly different shadow. However, as I have said, R omega varies from a large value to 0 continuously, so a precise shadow generously will be able to be achieved. But more importantly, our lensing analysis reveals that the degeneracy only holds in certain degeneracy conditions, which, in fact, are the same conditions or very similar conditions to the M80 star observations reported by the Event Horizon Telescope. So, which leaves us with one question for our first question. Are all shadows black holes? Well, taking into account our results, some of them can be Procastars. Thank you.
Okay, so thank you, Alexandre, for your talk. You were very generous with time, so we have plenty of time for questions. So again, I would call for any questions or comments, and these can be written in the chat if you want us to read, or you can just raise your hand. Well, I see no questions. So in that case, I think we will thank Alexandre again. Thank you for your talk.
Thank you.
And we will move on. Well, we are 10 minutes ahead, but I guess we should move on to the last talk of the session. So Fabrizio, I can see you. Can you please start sharing your screen?
Yes. Okay. Can you see it?
Yes, we can. So
Yes.
the last talk of this session is by Fabrizio Di Giovanni, and he's going to be telling us about a stabilization mechanism for excited fermion boson stars. So again, Fabrizio, you have the floor. Please go ahead.
Okay, thank you very much, Carlos. Okay, wait, my connection is unstable. Okay. Sorry. So I'm Fabrizio Giovanni, a PhD student from the University of Valencia. And today I will talk about two recent works that we developed in collaboration with Said Fakri, Nicolas Sanchez-Gual, Juan Carlos de Gollado, and Jose Antonio Font. And the topic of my talk is about fermion boson stars. So my idea was to start with a brief introduction on boson stars, but many other speakers already talked a lot about this, especially Nico. So here, I mean, it's the same thing that Nico said. We have a complex scalar field, and we consider this Lagrangian. Here I put the massive term in evidence, and we have a more general potential V of phi. Yeah, so like if we consider a real field, we don't have a stationary space-time, but so we need a complex field in order to have a stationary solution. So as Nick already said, boson stars are made of ultralight particles. And the reason why we need ultralight particles is because the ADM mass of the star is inversely proportional to the mass parameter of the bosonic particles. So we need a value less than 10 to the minus 10 electron volts in order to have a astrophysically relevant object. And here at the bottom of the slide, I am showing two plots. These are the domain of existence for a spherically symmetric scalar boson star, the plot on the left, and for spinning boson stars, the plot on the right. So looking at the plot on the left, I am showing the mass of the objects as a function of the central value of the scalar field. Yeah, this figure was taken from this work. And here, like, there are different lines because each line corresponds to a different value of a quartic self-interaction parameter. So as Nick already said, and also other speakers, like one can evaluate the maximum mass of these solutions, and from this, the point where the mass, this maximum mass happens is a critical value for the central value of the scalar field, which divide the unstable region on the left and the stable branch. Sorry. The stable branch on the left for values lower than this critical, and the unstable branch on the right. So going into the main topic of my talk, compact objects like neutron stars and white dwarfs may accrete bosonic dark matter. And the object that is known in literature as fermion boson stars. So these can be modeled by a perfect fluid, minimally coupled to a complex scalar field. The presence of dark matter inside fermionic stars can modify their physical properties, and these effects are possibly observable. The reason why I use a quotation mark is because the scalar field can well be inside the neutron star, but it can also be partly outside, surrounding the neutron star, depending on the model and on the mass of the particle, of the bosonic particle. So the construction of stationary solutions for fermion boson stars is a bit more complicated than in the case of boson stars, because it requires a so-called two-fluid model. Yeah, so and the results of that I'm showing in this talk are resumed in these two works. So I will briefly say some of the assumptions that we made to construct the equilibrium configurations. So we consider a spherical symmetric metric in Schwarzschild coordinates, and we consider a polytropic equation of state for the perfect fluid with a value of capital K equal to 100 and capital gamma equal to 2. We used units such as these constants are equal to 1, and we also set the bosonic particle mass equal to 1, at least for the models that I'm showing in this talk. And we consider a quartic self-interaction term in the scalar potential. Yeah, so as I say, like the construction of the equilibrium configuration require a two-parameter shooting method to extract the frequency of the field omega. So, okay, so in the second slide, I already said that there is a critical point that divides the stable and unstable branch for boson stars. The same happens in fermion boson stars. So here in these plots on the left, I'm showing the domain of existence. So instead of being lines as in the boson star case, the domain of existence is a surface, because we have two parameters: the central value of the scalar field and the central value of the rest mass density. So here I'm showing the results for three different values of the self-interaction parameter of the dimensionless self-interaction parameters, which is this capital lambda. I want to point out that in the case of negative self-interaction, the potential of the scalar field might break the weak energy condition. So for this reason, I plotted here this yellow horizontal line. So all the models above this yellow horizontal line for these values of lambda break the weak energy condition. So we are not considering these models in this work. But all the models below are safe. Yes, so what I was saying is that in the case of boson stars, one can find this critical value where the mass of the maximum of the mass, and it divides the stable and unstable branch. In the case of fermion boson stars, it is a bit more complicated to find. So instead of having a critical point, we have a critical line, which is this black solid line. And the way to construct these lines is to consider equal mass lines in the parameter space, which are these dashed colored lines in the plots, and monitor these two physical quantities, which are the number of bosonic particles and the number of fermionic particles, along the equal mass lines. And once you find an extremal point for both these quantities along the equal mass lines, this is a critical point, and it divides the stable and unstable branch. So we constructed different critical points in the plots, and we connected them and built these lines. So as I said, so the models inside these lines are stable, and the models outside are unstable. So in order to verify our results, we also performed fully nonlinear numerical evolutions of some models. So here I just show three different cases. So all these models are for a positive lambda equal to 30, and this central value of rho 1.5 times 10 to the minus 3 in our units. So here on the left, we have a case of central phi 0.03, and this model was inside the stable region. And in fact, during the evolution, we see that all the physical quantities are stable during the entire evolution. In the model in the middle, it lives in the unstable region. And what we observe is that it migrates to another configuration with a different central value of phi and rho. And what we can observe that during this migration, the number of fermionic and bosonic particles is more or less constant. And the last column is the same model as the middle one, but with a perturbation by hand of 2% of the scalar profile. And what happens here is that the model collapses to a Schwarzschild black hole. So here in the bottom plot, I am showing the mass of the apparent horizon normalized with the ADM mass of the system. So the model collapsed at around time 50. So another dynamical scenario that we considered is the dynamical formation of, so to do this, we considered a neutron star equilibrium model, which is surrounded by a dilute cloud of scalar field that accretes onto the neutron star. And it may form a fermion boson star. So again, we consider a polytropic equation of state as before. And we considered a Gaussian radial profile and an harmonic time dependence for the scalar field. So this is the shape of the scalar cloud. So intuitively, this process can lead to two possible outcomes. So either we form a fermion boson star, or the model collapse to a Schwarzschild black hole. So in these figures, I am showing, this is kind of a visualization of the formation process. So here I'm depicting the mass or the energy in the scalar field contribution of the energy at different, in spheres of different radii. So 10, 20, 30, and 50, and the total one, which is evaluated by means of this integral. So one can observe that at initial time, we have a well-diluted cloud, so a very distributed mass distribution. And then during the evolution, we reach a point where we formed more compact objects, and we have a kind of bounce here around 1000. And then like all the curves like converge to each other because the object is like radiating scalar field and it's converging into a static solution. So here I'm showing for this particular model for this cloud with these parameters and this neutron star. I am showing the late time snapshots of the evolution of the dynamical formation. And we could appreciate that, so this is the radial profile of the scalar field. And we could appreciate that, that the scalar field is like radially oscillating around a configuration that is this black, it should be like a dashed line, but it's not really clear, but it's this black line is a static model that we built with the initial data code. And so we can appreciate how this model is oscillating around this, I mean, how the curves are oscillating around this model. And also like the physical quantities, like the number of bosons, the mass, correspond very well with this model. So below there is just a 2D visualization. Furthermore, like I am showing here another case, like another model with these parameters. So here, this is for a positive self-interaction. So what we observed is that surprisingly, during the dynamical formation, starting from a Gaussian cloud, we formed an object, a fermion boson star, that had one radial node in the profile of the scalar field. So this was surprising because so boson stars have there are family of solutions of boson stars which show one or more radial nodes in the profile, But these solutions are known as excited states. So the ground state shows 0 nodes. And these excited states for boson stars are known to be dynamically unstable. So they either collapse or migrates to the ground state. So this finding that we observed in our first work suggested that motivated us to continue further investigating these models, and we tried to. So what we did is that we considered excited states for fermion boson stars. So we constructed again the solutions, and we tried to assess the dynamic, the evolution of the stability of these models. And another reason why we were motivated by to do this is because there was a similar results were shown in a previous work by Bernal et al. Where they studied what they called multi-state boson stars. So basically, these are boson star models composed by two coexisting scalar fields in the one scalar field in the ground state and one scalar field in an excited state. So they observed in their work that some of these models, if the number of bosonic particles in the ground state was higher than the number of bosonic particles in the excited state, they found that these models could be were stable. So motivated by all these results, we decided to study the excited fermion boson stars. So I want to point out that as there is no direct interaction between the perfect fluid and the scalar field, this stabilization mechanism must be purely a gravitational effect. So in this slide, I'm showing the same existence plots as before, but in in these plots now we all have models with one node in the scalar field. So our first excited state. So again, I'm showing in this scale of colors the total gravitational mass and the stability. So here I'm depicting again a black line that is the threshold between stable and unstable region. And the stability of these models was evaluated by means of nonlinear numerical evolutions. And in the last plot, there are 3 colored crosses. And these are models that we were able to form dynamically for a generic bosonic cloud. Okay, so in the work, I told you already that in the work about multi-state boson stars, the authors found that if the number of bosonic particles in the ground state was higher than the number, I mean, the numbers of bosonic particles in the ground state and excited state was connected to the stability. So we decided to investigate for our models if the ratio between the number of bosonic particles and the fermionic particles had a relation, it was connected to the stability of the models. So in this plot on the left, I am showing the ratio between NB over NF for models which are living at the threshold on the black solid line. So models that are like living at the edge of the stability. And what we were expecting was to see like a constant value, like it happened for the multi-state boson stars. But apparently, like the relation that we find is not as simple as in the case of two coexisting scalar field. So what we can observe here is that we can see an initial. So here there are like different values of self-interaction. And we can observe that for all cases, we have an increasing monotonical behavior of NB over NF up to a certain threshold value, critical rho. And this threshold value is not the same for each model. And then we have like a saturation regime where the number of, where this ratio is more or less constant. One thing that I should point out is that we observe that for low values of the self-interaction, so -30, 0, and 10, there is a drastic drop in this quantity exactly when at this critical value of rho. And this drop seems to be disappear if we consider models with higher self-interaction. So here I want just to show a few results of the evolutions. So here I'm showing one model that we evolved. We evolved more models because we had hundreds of models. But this is one example of a model that at initial time is a one node configuration. And during the evolution, as this model is unstable, it migrates to the ground state solution without nodes. And then I want to point out again some other results about the dynamical formation. So again, I want to stress out that here for the dynamical formation, we start with a Gaussian profile for the bosonic cloud. We don't put any node in the bosonic cloud, so it's a very generic cloud. And for some models, we were able to observe in the final state of the star the presence of one or even more than one nodes in the scalar field. And another thing that we checked was we evaluated a fast Fourier transform of the real part of the scalar field. And from this fast Fourier transform, one can extract the frequency of the scalar field. So what we see, for example, in the model on the left, this bottom plot, we see that there is an evident peak on this frequency 0.76, which corresponds to this model that I'm depicting here, like these dashed black lines. So it's the frequency of the first excited state. And all these other vertical lines are the frequency of the same model with same central phi and same central rho, but in the ground state, in the second, third, and fourth excited state. So as you can see, there is kind of like small peaks that correspond to these values of omega. And this is more evident in the second model that I'm showing, where you can see that basically there is like a superposition of the more states of this star. So what we suppose it's happening here is that the newly formed objects is suffering radial perturbations, and due to this perturbation, the scalar field oscillates between different states. So between the ground state and the first, second, third excited state. Okay, so yeah, I'm done with fermion boson stars. I would just want to add a few things about another recent work that Nico already said something about it. So this was led by Nico, and it's multi-field, multi-frequency bosonic stars. So in this work, what we did was considering some models of boson stars, which are composed by a set of scalar fields, which are described by this formula here. So for each value of L, we have 2 times L plus 1 scalar fields, which with different values of the azimuthal number M, that goes, it's an integer value that goes from -L to +L. So, well, very similar to the hydrogen atom, for example. So, yeah, or the, yeah. So in this figure here is a very nice representation of the L=1 boson stars family. All the models which are living on the perimeter of this triangle have are models where we assume that the frequency of the 3 fields is equal. So this omega, instead of being omega j, is just omega, and it's the same. So here at the corners, the bottom corners, we can see like the spinning boson stars, m = -1 and m = +1, which Nick already showed in his talk, that these spinning boson stars were unstable and they were decaying to the L equals 0 spherically symmetric boson star. And then like we added this new solution, like this dipole solution, which correspond to the M equals 0 case. And we found that also this solution was decaying to the L equals 0 spherically symmetric star. So on the sides of the triangle, there are models which are mixed. So like they have two fields, like the twos that are at the corners of the side. And then at the center, we have the L boson stars, which is a particular case where we have the three fields with the same frequency and multiplied by the corresponding spherical harmonics. And in this case is very particular because the metric and the stress energy tensor is spherically symmetric. So all these models that are living on the triangle, well, the models inside the triangle in the blue area are models where we relax the condition about omega to be equal. So they are multi-frequency. So all these models living in this triangle are unstable, except for the L boson star, which is stable. So what we did next was to consider like hybrid multi-field, well, hybrid L boson stars, let's say, hybrid multi-field stars, where we combined the L equal M equal 1 spinning boson star together with a L equal M equal 0 spherically symmetric boson star, which is the ground state of all the families, and it has a stable branch. So if we combine the two of them, we observe that if the contribution from the spherically symmetric boson star is higher than the other one, we can have a stable model, as you can see in the top of this the time evolution at the top of this slide. And if the model is closer to the spinning boson star, which we already assessed that was unstable, also the model is unstable. Well, yeah, in conclusion, I will just read the future work because I don't know how much time I used. So yeah, we plan to consider more realistic equation of state and studying the effect of the scalar field on the neutron star physical properties. And another interesting thing would be studying the fermion boson stars in rotation. So thank you very much.
Okay, thank you, Fabrizio, for your interesting talk. And again, we still have some time for questions. We ended up a bit earlier, so we still have 12 minutes until the set time for the end of the session. It's been a longish 3 hours of interesting talks, though, I would say. I'm not sure people are still full of energy to ask questions, but let's try. If there is anyone still kind of with sufficient energy for wanting to know more. So are there any questions?
It's a bit late for European.
I guess. Well, at least here, I guess for some people it's kind of early in the day, but late in the number of talks, like I guess who's in Mexico. But
yes.
Anyway.
And one thing, Carlos, please don't forget that every day at this time, you should get the passcode for the next day. Yes.
Yes,
that's right.
Each day has a particular passcode, and you should get the passcode one day in advance at this time.
That's right. So I've just checked and I've got the email with the passcode for tomorrow.
Yes, I got it. If someone didn't get it, you should write an email to me or to Carlos, and we will provide the passcode for the next day, especially for Thursday, the second block of the session.
Exactly. So don't forget that on Thursday, we'll have the second block of our BS1 session. That will be at the same time as today. Well, in any case, there's a question actually. So there's a question by Dawood Rafiai Kirk-Vendi. So please go ahead.
Hello, and thanks a lot for your presentation. My question is about the capital lambda that you choose equal, I think, to 30, and in some cases 30, 10, and also 50. Could you please let me know that what is the reason that you choose these cases for capital lambda, which is also has relation to the lambda, which is the coupling of the in fact self-interaction, or also mu, which is the mass of the boson, in fact?
Yeah, so actually, I mean, there is not a very interesting reason, I would say. I mean, there was a previous work on fermion boson stars, and we were working on the same project while they were developing this. So Susana Alvarado, she worked on this topic in the case without quartic self-interaction, and then she also worked in a case with positive self-interaction, and she used also this value lambda equal 30. So that's why we decided to use this one. In general, I mean, this is a value that I think it was used also for boson stars before, like.
No, the Colpi article, I think.
Sorry, what?
Which the Colpi paper that you showed.
Yeah. In the Colpi one, they use a lot of values, but the thing is that in the Colpi paper, these central values of phi is defined in a different way than our, because it has 4 pi inside, I think. So I don't remember if the definition of lambda in their case is exactly the same one. Probably yes, but I'm not sure 100%, because I mean, it's something that I checked before, but I don't remember, because I also did these checks for boson stars to see if we were obtaining the same results as Colpi. But yeah, that was just the reason. I think that in their case they went way up with the value, but I mean, the only more interesting thing is that maybe you have the appearance of this second branch here, if you consider higher values of lambda. But as I said,
I have seen in some papers, for example, written by Joshua Ibai, I don't know, the Boson Star, right? That, for example, they use another parameterization for the lambda, which is related to the self-coupling. For example, lambda should be less than 4 pi because of the, for example, if you want to work with the masses equal to, for example, 100 mega electron volt. Or also, for example, in another papers, which is with the model of the Colpi is used for darkest stars. And again, there are some reasons that they use the coupling constant, for example, about pi, half pi, and 2 pi for some special cases of masses. Then my question is about do you have any idea about that? For example, the relation between choosing the coupling constant and the mass of the boson, especially with the parameterization of pi.
Yeah, I understand your point, but I didn't know about this, so I'm not really sure what to answer. I mean, I would be happy if you could send me the references of the papers that you are saying, so that I can read the reasons why they use these particular values for lambda. In our case, we just consider some. I mean, we didn't have a proper idea of what. I mean, as we don't have observations of these objects, we don't really have an idea of the scale of this self-interaction if it exists. So that's why we chose these values. But in any case, I would be happy to listen to read the references that you were suggesting.
Thank you very much. Thanks a lot.
Thank you.
Okay, thank you for your question and the reply. I don't see any further questions. So at this point, maybe the participants would like to turn their cameras on and join me in a round of applause for not only Fabrizio, but all the speakers of this session that have kept the time and gave us very interesting talks. So thank you very much. Okay, and then I think that we are done for today. Alfredo, would you like to say anything to conclude?
No, see you on Thursday. Thank you for the nice and interesting talks.
Okay, so see you on Thursday. Don't forget that we'll have another session starting at the same time. And see you then and enjoy the conference.
See you on Thursday.
Bye, everyone.
Thank you.
Bye.
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 Bye bye. See you.
Thank you. Bye-bye.
See you.